Okay, I'm going to continue with Chapter 5. Now, Chapter 5 is all about e to the x. And again, I want you to keep in mind that e is just a number. It's essentially just 2.71. But it's a special number. But whatever you do, don't consider it like a variable. When you're finding the derivative of it, it has to have an x in there somewhere. Otherwise, the derivative of just e alone is like any number. The derivative of e alone is 0. So don't get freaked out by e, and also realize that as a growth curve, that's the same as 2.71 to the power of x. I know there's more numbers here, but all e is to the x is a growth curve, and it follows the same rules of the growth curve. 2.71 to the 0 when x is 0 will be 1. When x is 1, it will be 2.71 as the y value. When x is 2, it'll be 2.71 squared, etc., etc. It's just a growth curve. And I've posted above proofs or easier ways to understand the derivative of it, because your textbook essentially just says, well, the derivative of e to the x based on x is simply e to the x, and you're going to have to trust us. And the most they do is they tell you to take a standard derivative formula like this, and they just tell you to have a look at different values of x, so you can see that its rate of change is the same as its y value here. And they just ask you to just constantly notice that. So notice the y value here and the rate of change here is the same. And that's pretty much all the textbook does for e, which is sort of unfortunate. And then it's going to move on to any number to the power of x and combinations thereof. Comparing the graph of the exponential function with the derivative. Solving optimization problems. Then we're going to move on to sine curves, tangent curves, and the derivatives, and solve rates of change for those. Now, the problem with some of the derivatives, like the sine derivative, requires additional derivatives to understand, and the tangent and the cosine are just related to the sine derivative. So I urge you to spend time on YouTube if you want to see proof, because in my opinion, understanding how you get from point A to point B makes math a lot easier. Okay? For instance, we've learned quite effectively that the overall formula that we learned from functions is essentially a derivative, so that's an important step. And then we also learned, the power rule. And we learned that the power rule led to the product rule, and the product rule led to the chain rule, and the chain rule led to, and the product rule also led to the quotient rule. And the more you understand the connections, the better it is. So I urge you to try to look up from basic proof of all these things, because your textbook, in this case, doesn't do it. They're going to go through some basic skills, but they also want you to remember the properties of an exponential function. That's important. And various truths. So, for instance, when it's b to the m is equal to n, it's the same as saying log base b of n is equal to m. What the hell does that mean? Well, that means you want to understand what a log is. And a log is the reciprocal of an exponent. So if I have 2 to the 4 here, that's clearly 16. Sorry, 4, 8, 16, yeah. Now, if I want to phrase that in terms of log, I would say, I'm going to leave that there. I'm going to say log, what number do I have to put 2 to as an exponent to get 16? And the answer to this is 4. So you want to make this clear connection of where these numbers go, because it's totally related. So again, the log is essentially saying, what exponent do I have to put to the power of 2 to get 16? And it's clear that that's 4. This one is essentially saying 2 to the 4 is what? 16. But they're intricately related. That's precisely what a log does. It's all going the backwards reciprocal direction, essentially, of an exponent. It's kind of like if this is multiplication, this is division. And that's important to understand. And all they did in the textbook is they said, well, when, actually leave that up because it'll help you. In the textbook, all they said, well, try to remember that b to the n is equal to, essentially, b to the n. It doesn't really help this way. But then over here they said, try to remember that log base b is going to be b to the n is going to result in n. And I think they even just changed this, said, well, if m obviously is equal to n, we would say b to the m, but it doesn't matter what. They're essentially putting it in generic terms, but this is a lot easier for students to understand. Let's go into the basics. Oh, and for trigs, you're going to have to remember how to convert radians if you haven't already. It should have been in functions 12, but we know a circle is 360 degrees. And we also know that that measures sort of the internal angle in here. Radians measures the outward circle out here. So if I had to figure out the total radians around the circle, and remember we used radius 1, well, you know that the circumference of the circle is pi times r times 2. But obviously if radius is 1, it's just 2 pi. So that means in radians around the unit circle is 2 pi radians, like that. And that's the same as 360 degrees. It's just that the radians measure the arc out here, and the degrees measure the angle in here. But they're directly related. So that's important to understand. Obviously, if 2 pi is the full circle, half the circle, which is 180, is going to be pi. So that's important to remember. And that 90 is going to be half of the pi, just as it's half of 180. So it's pi over 2. Get very comfortable with this. So essentially, whenever you have 360, and you want to convert to radians in pi radians, you're going to divide it by 360 and multiply it by 2 pi. And the short form of that is, obviously, pi over 180. So if you want to convert to degrees, you multiply it by pi and divide by 180. The reverse is true. If I have 2 pi and I want to get to degrees, I want to multiply by 360 over 2 pi so that this cancels out and I get that. Or the short form is 180 over pi. And this way, the pi will cancel out, and I'm left with 2 times 180, 360. So remember, it's very easy to figure out how to convert, and you should be comfortable on all the major trig identities. All right, what else does this book cover? They want you to remember what the sine and the cos curve looks like, and what their period is, and what their amplitude is, and what the tangent function looks like, and where it has asymptotes and why it has asymptotes there. And they want you to remember your basic trig identities. Now, obviously, some are easy, like these. Some require a little bit of maneuvering, but they generally come pretty easily. And then some are from Pythagoras' theorem, and these are also easy to prove. This one's very easy to prove. It leads to this one and leads to that one. And this is just simpler than it looks, reflection identities. And I'm not even good at reflection identities. I don't bother. But if you look at it carefully and logically, one at a time, they're just saying, if I have a negative angle here, and I go over negative pi over 2, the sine value of this whole thing is going to be the same as negative sine of when I went this way. So they're just saying it's opposite. If you're looking at a negative angle, you can just take the normal sine of whatever that angle is and then just slap a negative into it. So if this comes out as negative, you have to multiply by negative and it'll become positive. Seems weird until you just look at the dynamics of it with examples. Same with this one. This is saying, well, the cos of a negative angle this way is the same as just the cos of the angle up here. This becomes more clear when you realize you're dealing with x values here when it's the cos, because cos comma sine in terms of the unit circle, the cos represents the x values, and it's clear that when x is positive here, it's positive here, and when x is negative here, it's negative here, which is why the cos of the negative angle is the same as the cos of the angle. This is just saying, try to remember that there's a connection between cosine and sine within 90 degrees, and that the sine of this angle here will be the same as the cosine of this angle here. There's that connection of 90 degrees, which is pi over 2. No matter where you are. They're complementary. Or is it supplementary? And then it wants you to practice your basic skills, which I'm going to race through, because you really don't need too much here. As for proof of e to the x, there's not a lot of good ones out there. I've included one that I feel is intuitive, which uses implicit differentiation, which I actually feel is pretty good. Okay, what does 3 to the negative 2? What does it negative 2 even mean? Well, I'm just going to do that. Negative 2 simply means if it's in the numerator, it should actually be written like this. So the negative 2 just sends it to the denominator with a positive 2, which of course is equal to 1 over 9, and that's the evaluation. The same falls for when it's in the denominator. This is the same as this, which is the same as 9. So be aware of that. Negative just means we're switching from numerator to denominator or vice versa. What does this mean? Well, whenever you have a fractionary exponent, remember the top part represents a power, so 32 squared, and the bottom part represents a square root, but in this case, instead of a square root, it's a 5 root. So you can go either direction. You can either square it first, which you can quite clearly see is the more difficult root, or you can go the square root. And just keep in mind, square roots are to exponents that multiplication is to division. Okay, so what number would I have to put to the power of 5 to get 32? Clearly it's 2, because times 2 is 4, times 2 is 8, times 2 is 16, and times 2 is 32. So the answer to this part is simply 2. It's much easier now to square 2 and get 4. Had I squared this first, I'd have a huge number, then I'd have to pull out my calculator to evaluate it. Whereas this one, I could do it in my head. Sometimes it's important to figure out which route to go. What about this? Well, the same thing. What about the negative number? Okay, let's start by getting rid of that. That's all that means. It's going into the denominator. Let's focus on this part. Should I square 27 first, or should I see if there's a cube root of 27? And there is indeed a cube root of 27. It's 3. 3 times 3 times 3 is 27. So that means this thing at the bottom, 27, is actually the same as 3 squared. It's clear that 3 squared is 9. So that is the answer to that. What about when it's like this? What do I do? Well, there's a nice little trick with this that I'm going to show you right now, which is you can just flip that fraction and make it squared, which is the same as 3 over 2 times 3 over 2, which is 9 over 4. That's the answer. But you can also do it individually if you're not dealing with easy terms like this one. Just remember, exponents for divided or multiplied numbers can be shared with the specific exponent. This 2 to the negative 2 says it's going to send it down here, and this 3 to the negative 1 says it's going to send it up here. And you get the same result. What about this? They want this as a log. Well, that's one of the reasons I did that explanation for you, is because this is very easy to change if you remember the sheet I gave you. So it's easy to start with a simple example. This translates into this. What do I put 2, what do I put over as a power to 2 to get 8? 3. So that means the result goes in here. Well, here's the result. That means the base comes from whatever you're putting to the exponent, log base 5. So this is saying, what do I put to a power of 5 to get 625? And you put equals 4. 4 is what you put to the power of 5 to get 625. So if you have a map like this, you can just follow the same rules for this. So the 5 is going to go as the base. The 4 is going to go as the answer. The 625 is going to go as the question. These all have terms. I forget them right now. And I think it's close to base and things like that. But you'd have to look that up. What about B? How do I prove this? Or how do I put it in logarithmic form? Well, it's the same thing. You go back to your map. This is the same as log base 2, 8 equals 3. All right. This is the answer here, so it's going to go there. So I'm looking for the log of 1 over 16, but suppose I don't want to express that as 1 over 16. Well, I can do 16 to the minus 1 if I want. And then over here, this 2 went as the base, so this 4 is going to go as the base. So this is essentially asking, what do I have to put to the power of 4 to get 16 to the minus 1? Or if I want to keep it in the other format, I might as well, since they didn't ask me to simplify it. What do I have to put to the power of 4 to get 1 over 16? Well, minus 2. So that means the log base 4 of 1/16 is minus 2. Understanding this is much better than using a calculator. Just understand the mapping that I did here, and things get a lot easier. Then work on your speed. Work on how fast you can convert that. Okay. Oh, and by the way, I should keep my map. I'll just keep my map, and I'll get rid of these. Okay. Well, what's my base? It's the x. So log base x. What's that? That's going to be my answer. And this is going to be this. So they're saying, what do I have to put to the power of x to get 3? And in this case, you should be able to solve this. If I take the cube root of x, I don't know if they want you to solve it, but this can also be rewritten as the log of the cube root of x for 3 is 3. In other words, how do I get x cube root of 3 to 3? I put a 3 over it. No, I actually shouldn't say cube root of x. I should say cube root of 3 down here. So if I'm going to solve it. Okay, let's keep going. What about this one? And again, they're just asking you to keep things in. They're not asking you necessarily to solve it, unless they say evaluate it. No, they just say express as logarithmic form. So again, my 10 becomes my base. I'm looking for 10, log base 10. So I don't need to write that because log is naturally base 10. And then my answer is 450, so that goes here because my answer here went there. And then equals W. So what do I have to put 10 to the power 2 to equal 450? In this case, they're telling me W. Now you can actually solve this, and you'd have to take a log of both sides. This is now to the W, so it can go in front. So I get W times the log of 10. What's the log of 10? It is 1. So W is equal to the log of 10. Now, look how it came back to exactly what we're looking for, because Well, it's essentially rearranging it. It's essentially taking the log process to get to the log formula. But we could actually solve this. We could find the log of 450. And that's what W is, 450 log. W is 2.65. So in reality, we would say, what is the log of 450? It's 2 point whatever I had there. But they're just leaving it as W. Since they don't ask us to evaluate it, they're just asking us to rephrase it in terms of log. This, if you wanted to do it the long way, do log of 3 to the 8. The 8 can go over here, is equal to Z, and then you just divide it by 8, and this is one way. If you this method expresses it as a log of 10. So it's saying the log base of 3, 10 base of 3 is equal to Z over 8. But they don't want us to do that. They want it as a base of 3. And so it's interesting to notice that connection. So if I'm going to write this in log format, I'm looking for log base 3. What number do I have to put over 3 to get Z? Well, in this case, they're telling me it's 8. They're telling me a rule here, so I'm just rewriting it in log format. What about when it's all variables? How the heck do I do that? It's the same process. You have to just recognize what's going to become the base. This A is going to become the base. Log base A. This T is going to go here, and it's B, which is essentially what do I have to put over A as an exponent to get T? Sketch the graph of each of the functions. Interesting. This, you just have to know back to your parent function. This is the reciprocal of a 10 to the power of x. I'm going to skip the x plus 2, because it's actually x plus 2 up here. And I'm just going to realize that x plus 2 shifts the entire graph, every value of x, 2 to the left. And for that, I'm going to start with the parent graph. Well, there's a couple values I know for 10 to the x. When x is 0, this whole thing, normally 10 to the x comes out as 1. So when x is 0, it's going to be up here at 1. So it always goes through 1. I'm going to fix the x's in a second. When x is 1, it's always the base. So I'm always going to have the point 1 comma the base. And finally, when x is 2, we can go ahead and do that if we want. It's the base squared. So we have 3 nice points. But I know that x is going to move 2 to the left. So I'm going to take all my base points, and I'm going to move each x subtract by 0. So that means this new point is going to map out to 0, 10. And this new point is going to map out to -0, 100. This second map part is going to map out to -1, 10. And this last one is going to map out to -2, 1. The nice thing about reciprocals, which this log 10 base 10 x plus 2 is I can just switch the numbers and switch the domain and range. Well, the domain and range of this didn't change from a basic parent function because I didn't elevate it or shrink it. So that means for the domain it goes on forever, but the range here is above 0, which means when I find the reciprocal, the range, or the domain rather, must be above 0. You must switch your domain and range. Now, if I look at those numbers I found, I can just take a quick graph, and I'm going to realize that the graph is going to do something like this, probably, because it's a reciprocal of that. And all reciprocals go through y is equal to x. And I'm just going to take these numbers. So, it wasn't, it was 0, 100. Now, that means 100x, 0y. And you might say, how come it's going through, that's another thing. So, this domain has shifted 2 to the left. So instead of x must be above 0, it must be above -2, because the domain shifted as well. Let's see if that's true. So I'm looking at one number here. It's not 0, 100. It's 100, 0. So it's way over here. I'm looking at a number here, minus 1, 10. So when x is, oh, I'm getting this way. Yeah, 100, 0 is way over here. So this is going to be 10, minus 1. So it's going to be here. Or is it x smaller than plus 2? Well, I'll figure that out in a second. I'll go back and figure out the domain. And then this last one is going to be 1, 2. Yeah, this other one is not. It's going to be 10, minus 1. And this, sorry, is going to be, it's not minus 1. It's going to be 10, 1. And this last one is 1, 2. Interesting. Is that really it? Let me go to Desmos really quickly to see how or if I screwed that up. And if I do 10, oh, I know what I did. The reciprocal of 10 to the x plus 2 is not log 10 plus 2. The reciprocal of that I have to switch my x's and y's. So the reciprocal of that will not be that at all. It'll be a graph pushed downwards. So when I switch my x and y, I get this. And you should learn how to take reciprocals. Now, I can just plug in some x values, and actually that might be easier. But I have to choose careful x values. I'm first going to go back and see if I can find the reciprocal of it. I'm trying to solve for that, right? To solve a log, you're going to have to look and divide this up, because log base 10, if we're going to go to is saying 10, it's saying 10 to the power of x is equal to y plus 2. That's what it's saying. That's the basic of it. That's what a log is. And then you're going to have to say y is equal to 10 to the x minus 2. So there's my mistake, is that x translations in this one become y translations in the reciprocal. My bad. Which means those same values I found, which were 0, 10, 0, 1, 1, 10, and 2, 100, should have y subtracted by 2. Should have y subtracted by 2, which means all these y values become this. Those will be the opposite values. And if I sketch those, I get the opposite values will be 98, 2, 8, 1, 0, minus 1. 0, minus 1, like this. Keep in mind that because the other one, its range was bigger than minus 2, this one's domain must be bigger than minus 2. So that means it's going to pass here and have a minus 2 as a vertical asymptote, and it's going to do that. My mistake. Now you can also sketch it if you want. You can just put in values for x, 0, 1, 2. The problem with that is 10 to what power is going to make 2 is going to be a really tiny fraction. So you're going to have really strange numbers if you do it that way. Your best method this way, I actually prefer figuring out the reciprocal so I get an idea of what the graph looks like. But if I'm going to find a log base 10, I'm going to take some simple numbers here. So when is 10 to the 1 going to be equal to x plus 2? In other words, when is 10 to the 1 going to be equal to x plus 2? Obviously when x is 8. So I'm going to have a nice number there that is 8, 1. And then when is log 10 going to be equal to 2? Obviously when 100 is equal to x plus 2, which means when x is 98. We have a nice 98, 2 there. you can see that this came up with the same values. However, I feel finding the reciprocal was better. Let's have a look at what that looks like on Desmos. It'll be a lot easier. So this whole thing is this, and according to me, the reciprocal will be, oops, I don't know what happened there, will be just when I switch my x and my y's, will be like that. So you can see that they do indeed still reflect through this line, they just cross over so a couple points. Turning off the graph here, and to make sure I got the right log, this purple graph now and this graph should be the same. And they are. So this, which is clearly the reciprocal of that, is the same as this one here. So they are indeed reciprocals. I could always take some values of them and get some ideas. But you can see some of these numbers, as I said, will be so small you won't be able to graph them. Whereas if I take big ones like 98 and what was another one? 8. Yep. And what was another one? -1. You can see we get very clear numbers. Easier to map like that. So I did indeed get it right. Now I'm also going to put in the asymptotes here. There's the asymptote for the red line. And I'll turn off the purple just to show it. And here's the asymptote for the purple line. And I'll turn off the other purple lines and turn on the graph to show it. Sorry for the confusion, but maybe it was for the best. And then sketch a graph of this. So that's a standard exponent one. You just first figure out your parent graph, and then realize all your x values will be shifted to the left by 3. That's because x values do a different. You could have also, by the way, if you knew the log of 10 here, you could have graphed the log of 10 and then just shifted all your x values to the left too. 5 to the x, that tells me that when x is 0, this would be 1. I'm just looking at this, the parent graph. When x is 1, you get 5, and when x is 2, you get 25. Now if I shift all my x values to the left by 3, this becomes -3, this becomes -2, this becomes -1, and I could easily graph it. -3, 1 is here, -2, 5 is here, and -1, 25 is here, and it's clear the graph just shifted to the left by 3. It would also help to find out where the y-intercept is, and it's clearly 0, 1. So it's going through the y-axis when x is 0. So that'll help you as well for the parent graph. How about for this one? Well, when x is 0 here, 5 to the 3 is 125. So it's going through the spot 0, 25 at the y-axis for that. Refer to the following figures, state the value of each trigonomic function. Okay, so you need to remember your Sohcahtoa. It's very important to remember your Sohcahtoa. And here they're giving us x and y values, and they're just telling us it's a radius of this. Sine theta is simply equal to the y values, if you want to know. And cos theta is simply equal to your x values, if you want to know. And that's for when r is 1. But when r is not 1, you have to look at it as a triangle. So let me just pull that up as a big triangle. Okay. And then I'm going to draw it down to the x-axis like this and like this. And clearly the height of this is y. The length of this is x. And r is the radius. If I want to find the sine of this, the formula for Sohcahtoa is opposite over hypotenuse. Well, the opposite here is y over r. So if r is 1, you don't have to include the r, but when r is an r, you have to include it. And obviously, cosine says the adjacent over the opposite, so that would be x over r. So technically, unless they tell us r is 1, these are the actual ratios. And it all comes down to right angle triangles. These things are all things you need to remember. Convert the following angles. So that's pretty much what I was doing before. And it goes like this. I'll copy both these down. How do I convert 360? Whenever you want to convert something, I'll do both these angles here. Whenever you want to convert something, just remember you're trying to get rid of a 360 if you can't remember the formula. And you're trying to create a 2 pi because that's what a full circle is. But it's clear that this is going to be pi over 180. And then you go, oh yeah, that's the ratio. 180 goes into 360 twice, but we already know 360 is 2 pi. Well, same with this. We're going to do this over 180. This time 45 can't be divided by 180. 45 goes into 180. This disappears and it goes into 180 4 times, which means 45 degrees is the same as pi over 4, which makes sense because pi is 90 degrees. Oh, yeah, pi is 180 degrees. Pi over 2 is 90 degrees, which makes sense that half of 90 degrees would be pi over 4. Next one. Same conversion. Doesn't matter if it's minus. We're going to multiply it by pi over 180. It's clear that this goes in negative 2 times. So you get negative pi over 2, which makes sense. It's the same as this. This is negative pi over 2 in radians and negative 90 degrees in angles. That's what a radian is. It's the arc length around the circle. What about this 30? Well, we have to multiply it by pi over 180. 30 goes into this 6 times. So you get pi over 6, which means the angle 30 is the same as the arc radians, or the arcs, pi over 6, the radians. And also keep in mind there's always a little word here that I'm not writing in. Radians. These are all in radians. Your calculator won't write it in either. What about this? Same method. Over and over and over again. They just want you to get comfortable with it. If you're not comfortable, you need to practice more. So we're multiplying by pi over 180. They both lose a 0. This can be divided by 6. Or 3. I get 6. This can be divided by 3. I get 9. They can be further divided by 3. So they can both be divided by 9. This is 2. And this is 3. So I get 3 pi over 2 as the simplest fraction is 270, which makes sense because halfway through is pi, and another 90 degrees is pi half. When I add those together, it's 3 pi over 2. What about 180? Same thing. We're multiplying by pi over 180. We can knock off the zeros. Both of these can be divided by 6. This becomes a 3. This becomes a 2, which means we get minus 2 pi over 3. So minus 120 is minus 2 over 3 pi in radians. Well, they're going to get harder and harder. But the same process. You're just trying to simplify it down to the simplest fraction. And you never want to use decimals, even though you can use decimal forms for pi, because a fraction is far more accurate. Over 180. These cannot be divided in easily, but I can see that they're both divided by 5. So let's see what we get there. I get 4, 5 here. And down here I get 3, 6. Okay. I can see they both be divided by 3. Down here I can get 12. And up here I can get 15. Well, see, there was an easier fraction in there after all, because they can be divided by 3 again. And up here I get 5, and down here I get 4, and that's the simplest fraction, 5 pi over 4. So if you get stuck on a test, you can wind down those divisions like I just did so that you don't have to use your calculator if you're fast enough. What is this one going to be? Well, I multiply it by pi over 180. I can see that I'm going to knock off both the zeros. They can both be divided by 3. This divided by 3 becomes 11, and this divided by 3 becomes 6, and that's the simplest fraction, 11/6 pi. Now, I can take my calculator and divide those, and I'm going to end up with a really long thing, pi, but that's no longer accurate, and this is perfectly accurate to the exact number. Refer to this chart. So I'm going to just expand it over here. And I guess there depends which one they want to do. So they're saying this angle up here is the same as this angle, and this AB refers to this triangle, and this BA refers to this triangle. Okay, sine of theta, it doesn't really matter which theta we take, but I can tell you that the height of this is going to be B. And do they tell me? Oh, they even tell me that this radius is clearly 1 because the length up here is 1. So we don't have to use over r, where I will do it. Sine of theta in this case is equal to the opposite, which is b over r, but r is 1, so it's just b. Tan of theta is equal to the same as sine. Well, no, we can just use opposite over adjacent, b over a, because b is the height and a is the horizontal length of this triangle here. Okay. So these are all using your Sohcahtoa. What about the cosine? Well, that's adjacent over radius, which is 1. So that's just cos is equal to a. What about this? Well, this is one of those identities. Sine pi over minus cos is the same as cos theta, which just means what's the opposite angle of this? It's the same as the cos of that, and that just means that I need to use cos again, which we already discovered was a, which means sine pi, the opposite or complementary angle for theta here, is the same as cos theta, which is a. Same with this one. This is an identity, and we know that this is the same as sine theta, which we know is b. And finally, what about the reverse angle? Well, we'll try to remember that our formula for that is the same as minus sine of theta. That's our identity. We know sine theta is b, so we're talking about minus b. And that's a lot easier than it looks if you remember all your Sohcahtoa and your identities, which is why they reminded you of what skill sets you need. Okay, how about this? Let's just take 2 at a time. The value of sine theta, cos theta, and tan is given. Determine the values of the other two functions if pi lies in the given interval. The interval is very important. So, they're telling us it's going to lie between 90 degrees and 180 degrees. This is when you need your cast. C-A-S-T. In this case, they're looking for sine, and we can see that sine is positive here. We can see that cosine is going to be negative, and tan is going to be negative. We can also see that sine is equal to opposite over adjacent. Sorry, opposite over hypotenuse. So if I draw that out, I know that I have a 13 here, and I know my opposite is going to be 5. I just need to figure out what's my adjacent. Well, thanks to Pythagoras' theorem, I know that my adjacent squared plus my opposite squared is going to be equal to my hypotenuse squared. I can bring this over, and I get a squared is equal to 144. And I can quickly see that, oh, my adjacent is 12. And just keep in mind it's minus 12 if you want, because we're on this side of the x chart, and that'll help you figure out the signs over here. So now I have my minus 5. I know that cosine is minus 12 over 13. Adjacent over hypotenuse. And tangent is simply my opposite, 5 over my adjacent, minus 12, or rewritten, minus 5 over 12. Very easy once you slow down and realize these right angle triangles are the key to everything. What about this one? What's the range they're talking about? Well, it's very interesting here. They're telling me the value of cosine, and you should always also have your trig identities up in case this is a standard. Now, I forget, so I'm just going to use my basics. But they're telling me that this is going to be between 180 degrees and 270 degrees. So it's in this zone. And CAST tells me only the tangent's going to be positive, sine's going to be negative, and cosine is going to be negative, which is true here. It also tells me we're dealing with a triangle, and this is the angle we're talking about. It's always the angle to the x-axis. And since cosine is equal to adjacent over hypotenuse, I know my hypotenuse is going to be 3, and I know my adjacent here is going to be 2. I just need to figure out my opposite. Well, opposite squared plus my adjacent squared is going to be equal to my hypotenuse squared. So my opposite squared is clearly equal to 5, which means it's the square root of 5. And I just keep it like that. And just note that it's the minus square root of 5, because we're on the negative y values, and that'll help you remember your negatives over here. Well, sine is simply opposite over hypotenuse, 3. And tangent is simply opposite. Oh, sorry, they gave us, oh yeah, tangent is going to be, and you might say, well, why is tangent positive? Because it's going to be opposite negative divided by negative adjacent. So it's going to be minus negative square root of 5 over minus 2. And that becomes positive, so we just get square root of 5 over 2 is the tangent for this particular angle. They seem tricky, but they're not. They're Sohcahtoa and right angle triangles and Pythagoras theorem. On this one, they give us the tan, and they tell us, and we note the tan's negative, but they tell us we're dealing between 270 degrees. No, they tell us that the angle is between 270 and 2 pi, so it's over here. Well, we know C is positive and everything else is negative. So that means we just got to remember our C is positive, and we also have to realize we're dealing with a triangle in this quadrant. We also know that tan is opposite, so minus, just consider this minus 2 over 1 over adjacent. And that means our hypothesis is the square of this plus the square of that. So what's 1 plus 4? It's 5, but we have to square root it. So that means our opposite is the square root of 5. Now we have all our values, and we just have to remember that cosine is the only thing that's positive. And so that means sine of this angle is minus 2 over square root of 5. And cosine, the only other thing we're looking for, is adjacent over the hypotenuse. And it is positive because we're dealing with positive x and positive hypotenuse. So there you go. Not as hard as it looks, because it certainly looks like gibberish when you first see it. This one, they're looking for an angle that's all the way between 0 and pi. Now, sometimes when we're dealing with two quadrants, there's two possible answers. We have to look at our cast to see if it's possible. C-A-S-T. Well, the only thing they've told us is sine is 1, positive 1. And we know we're dealing between 0 and pi, which is there. And we know that sine can be positive in both, which means we're dealing with two possible angles. Since they're all positive here, that's important. But over here, cosine and tangent are going to be negative. Well, let's just work on our triangle. It doesn't matter which triangle you use. We just know sine is 1 for the angle. Sine is opposite 1, and we know it's 1 over here. That's interesting because we can't have that. Right away, I should have caught myself and said when we're dealing with sine of 1, the only way it can be that way, since sine is x comma y, and sine is the y, if this is a radius circle, the only way sine can be 1 is at 0 degrees. And that means over here, it's also 180 degrees. So that means not only that, but I've solved what the theta is. I also know the cosine for that theta on this side is 0. And on this side is also 0. And I also know that the tangent, and this is the interesting part, is sine over cosine. And since cosine is 0 both times, tan does not exist. So there's no solution for tan. Just to confirm that, I'm going to pull up number 7. These last two. And sure enough, we can look and see that it says right there, oop, that wasn't very good. We can see right there that it says tan's not defined. Cosine for this angle is 0. And it's interesting that they said pi over 2, because they also should have considered, since 0 is included in the angle, that cosine of 0 is also 0. Because 0 is definitely included as a possible angle. Okay. Onwards. Here they want you to remember the parent functions for cosine and sine of these things here. Well, they want the period and the amplitude, so that's fine. That's all we're going to focus on. Cosine period is normally 1. Sorry, amplitude is normally 1, and it's only affected if there's a number out here. When the number's in here beside x, it's affecting period. So right now I can tell you the amplitude for this is 1. So I just say amplitude is 1 because there's no number in front here. This affects period. The normal period for any cosine or sine is 360 degrees, or pi or 2 pi. That 2 doesn't mean I'm twice the period for x values. It means I'm half the period, which means my period is half of 2 pi, which is 1 pi, which could also be expressed as 180 degrees. What about b? This has two things affecting it. I can see a 2 outside here, so I know my amplitude is going to be multiplied by 2. So that means my amplitude, which is normally 1, is now 2. Now this looks tricky, but it's really a half times x. I know that my x multipliers are actually the reciprocal, so that means my period is actually 2 times bigger, not a half. Since my period is normally 2 pi, my normal period, my new period now is 4 pi, which is also 720 degrees. And that's how you figure that out. You have to remember that your x values do the reciprocal or the opposite direction. That's those two. What about this one? So technically they said the amplitude. So I shouldn't really care at all that they've moved the entire graph up. The normal amplitude goes from the normal range goes from -1 to +1. By raising it 1, I haven't really changed that amplitude. So really that's just a trick question. The amplitude here is still 3 because amplitude is always positive, even though it says -3. Now I know it goes from -3 to +3. If they wanted me to tell the range, I would increase these both by 1, and I get 4. and minus 2. But notice the amplitude is still 3. So since they only asked me amplitude, I would only answer 3. However, if they wanted me to tell the period or the range now, it goes from minus 2 to 4. Now, what about inside? This is the only thing that's affecting x. And I can see x is being multiplied by pi, but it does the reciprocal, which means my period is going to actually be multiplied by 1 over pi. Since my normal period is 2 pi, this is clearly pi's canceling out, and my period becomes a unit of 2. In other words, it's going to repeat every 2 units. This is good if you want to convert something to time. So every 2 seconds, the pendulum swings back and forth. And this is good to note that if you want to convert something to time, like the standard one is hours, seconds, day, 24 hours, in years, 365, that's how you do it. You have to include a pi in there. To convert, let's say I want to convert something to 365 days. I want to make it a yearly weather pattern. Well, since I know I start with 2 pi and I want to get to 365, I know I'm going to multiply it by 365 over 2 pi to cancel out the 2 pi's. However, I know this is my multiplier that's going to go beside x, except when I write it in the formula, it's going to have to appear as the reciprocal. So if I want to convert a sine curve to a 365-day graph, I would do it like that. Let's take Desmos as an example and show that this is true. First thing I want to do, though, is put it in radians. It is. Second thing I want to do is put up a normal sine curve. And note that even though it's in radians, I should put it in steps of pi over, no, not that, yeah, 1, but this in steps of pi over 4, let's say. That way it lists it in pi's. Now, that's great. Now I'm going to do the conversion I just said. What did I say it was? I have to multiply this by 2 pi over 365 to convert it to a 365 graph. So now, to see that blue one properly, I'm going to make my x-axis go from 0 to 365 so that I can see the blue curve properly, and I'm just going to turn off the red curve. I also have to convert it now instead to numbers so that I can see, sure enough, there's the end of my period, 365. I successfully created something that's in a 365 period. Why would I want to do that? Weather patterns, annual fires, let's say, if I wanted to track fires on an annual basis and see if they were seasonally related. If I wanted to track anything to see if it's related to the year. And it's very important to note that. Okay, stop that nonsense and look at this one. What's going on with this one? Let me get rid of everything else. This one, the amplitude is being changed by a multiplier of 2/7, which means the amplitude is 1 times 2 over 7. So that means my new amplitude is 2 over 7. But my period is not being multiplied by 12. It's being multiplied by 1 over 12. My normal period is 2 pi. It goes into there, and I get pi over 6. This is my new period. What about this? This is a bit of an odd one because they've actually given a translation, not a period change. The amplitude here has been multiplied up front by 5. So my new amplitude is 5. But the period hasn't changed. There's no multiplier in front of here. That's got nothing in front of it. It's just been shifted to the right by pi over 6. What is pi over 6 in degrees? Well, we can always figure it out by multiplying this by 180 over pi. These cancel out. 6 goes into 180, 30. So that's 30 degrees. The whole graph is shifted to the right by 30 degrees. That didn't really change the period. The period's still 2 pi. But now it's going to start at 30 degrees. So one period is going to start at 30 degrees, and it's going to end at 390 degrees, which is a 30-degree shift to the right. Put in pi terms, it's going to go from pi over 6 to 2 pi plus pi over 6, which is 12 pi over 6, which is 13 pi over 6. So it's going to go all the way over here to 13 pi over 6. That did not affect the period, just where it started and ended. And finally, this last one. What's interesting about this is all my y values will be positive. So if I have a normal graph like that, the new graph is going to do a weird thing like this. But my amplitude is still multiplier 3. So I'm going to have an amplitude of 3. And my period obviously has not changed. So my period is still 2 pi. Let's see what that looks like. There is the normal 3 pi. And I'm just going to go in close so we can see it. And again, it helps if I label it in steps of pi over 4 or 3. There we go. It's a little clearer, but let's put an absolute value in front of it. And that's what I get. Bouncy, 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 bouncy. All right, I'm going to have to, I think, pause here because I want to phone someone about it. Oh, no, there's only a few left, so I'll finish it up. Sketch. We're down here. Sketch over 2 complete periods. Now you can go into the minus if you want, but just realize this amplitude's been affected by half, so it's going to go 180, and the whole thing has been raised by 1. And that's the only thing that's happened. So if the normal one is this, 0, 0, and it helps to know the full spots. 90 is now pi over 2, comma 1. Then it goes pi, comma 0. Then it goes 3 pi over 2, comma minus 1. And it finally ends at 2 pi, comma 0 again. Like that. That's the sine curve. Well, this period is now going to go into halves, so I have to half all those peaks. And they're also raised by 1. So this 1 goes to 2. This minus 1 goes to 0. So what I have now, if my Cartesian is here, I'm going to start here instead of at the axis. I'm going to go up faster and down faster, and it's going to end at the axis. Up and down, and one more, and there, that's 2. Then if you're going to label it, this is not pi over 2 anymore, it's pi over 4. This spot here is not pi over 2 anymore, or sorry, pi anymore, it's pi over 2. This spot here is not 3 pi over half anymore, it's 3 pi over 4. And this pi spot here where it ends is not 2 pi, it's half of that, it's pi. On top of that, the y values are now 2, 1, 0, 1, oh, and I forgot, and then it repeats. And how you repeat it after that is you add a period to all these values. And since the period's pi, you add a pi to that, pi to that, pi to that, a pi to that to repeat all the values. But the y values will be the same thing. Let me show you that on a graph because Desmos will make it a lot more clear for you. Sine of 2x plus 1. And I'm just going to put the new axis there. The new axis is always how much it's elevated. And you can see there's the points I was talking about. Let me see. Let me just do them in order so that I get them. 1. There, I'll do the top ones. That way it'll do the and the bottom ones. And then I can do the middles. No, I have to do the outsides. Yeah. Nope. Yeah. I have to zoom in, I think, is what I have to do. And it's hard to see them individually like this, so I'll start at the beginning. 0, 1. There's the pi over 4, 2. There's the pi over 2, 1. There's 3/4 pi over 0. There's the pi over 1. And then they repeat. Then they repeat by just adding a pi to the x value. Get used to graphing. It helps to graph these things. You're going to do a lot of graphing. Okay, what about this one? Well, it's a cos curve. The period has not been adjusted, so it's 2 pi, but the whole thing has been pushed to the left. What is pi over 2? 90 degrees. The amplitude has gone up from there. So if I was to draw this, I know that a cosine starts up here, goes down, minimizes there, that's there. That's the halfway point. It helps to know the halfway point of your graphs, like that. I also know the new amplitude is going to be 3, so the peaks are going to be always 3, and the mins are always going to be minus 3, and these are always going to be at 0y. But I also know the whole thing goes over here. So while this is normally 0, 3, it's now minus pi over 2, 3. While this is normally pi over 2, 0, it is now 0, 0. This is normally pi, it is now pi over 2. So if I was to sketch it now, I would sketch it something like this. And repeat. Let Desmo sketch it better than me. There we go. And we're going to make the axis just at the 0. And sure enough, there's the start, there's the peak, there's the midpoint, there's the bottom, and notice all the x values have been shifted to the left by pi over 2. And notice the amplitudes are 3 and minus 3. It gets very easy to sketch these if you know the parent graphs really well. Prove the following identities. Okay, start with this one. This always comes down to your knowledge of what tan x is and whatever. So tan x here, I can sort of go over there. Secant x is the same as 1 over cosine x. So let's start with that. Secant x here is 1 over cosine x. Cosecant is 1 over sine x. Let's leave them like that for now. They're multiplying. This one over here, tan x, is sine x over cosine x. And it's clear to me that cotangent is just the reciprocal of that. Cos x over sine x. Now I have two choices. I can have it all equal to 1, or I can have it equal to one of these things. Remember that this is cosine over here. Let's multiply this right side by sine x. Essentially gets rid of this on this right there. And I'm left with 1 over cosine x. When I multiply it over here, I have to multiply both these things. It's clear I get sine x squared. That might not be the best. Actually, you know what? That might not be the best method that I just used. Let's work instead on getting the left side equal to the right side. And just remember that this is secant x. This is sine over cos, and this is cos over sine. If I'm going to add them, I'd have to cross multiply, wouldn't I? If I'm going to add these fractions, I have to cross multiply. Well, I get sine squared there, plus cos squared there, over cos times sine. starting to look familiar. Let's see if I want to add those two fractions. Well, sine squared plus cos squared is 1. Like that. And this fraction here can be divided up into 1 over cos x times 1 over sine x. And I happen to know the reciprocal of cos x is sine x. And the reciprocal of 1 over sine x is cosecant x. So I'm left with this. And they're equal. What about this one? Prove this one. Well, the bottom one's giving me a big clue, because 1 minus sine squared is the same as sine squared plus cos squared is equal to 1. And if I put the sine squared to this side, I get cos squared is equal to 1 minus sine squared. So that means I can replace all that with cos squared. One minus sine squared. Yeah, cos squared. Remember that. Cos squared. Well, I'm allowed to take this fraction up above, and I'm trying to equal this on the right. Well, this fraction up above is the same as sine x over cos times 1 over cos. If I multiply these out, I get that. Okay, that means I can replace this fraction with that fraction. Well, I happen to know that sine x over cos x is tan x. I happen to know that 1 over cos x is secant x. So I'm left with tan x times secant x. My left side equals my right side. Solve the following equations. A little rusty on these. Well, these are all going to use your knowledge of factoring. If I subtract sine x from this side, I get 3 sine x minus 1 sine x. That's clearly 2 sine x is equal to 1. If I divide by a half, I get sine x is equal to 0.5. To solve for x, I have to take the arc sine of sine x and the arc sine of 0.5 on both sides, and I'll be left with x is equal to the arc sine of 0.5. Now I know that this is actually an actual easy value that I should memorize, but I'm just going to instead 0.5, and I'm going to take second, I'm going to take the arc sine. 30. So I can tell you that 30, it's 30 degrees, and if I convert that, I know that that is pi over 6. So I should have remembered, and you should have your table of standard trig identities up. What about this one? Let's get our coses to the same side. So if I add a cos x to each side, I'm left with 2 cos x minus 1 is equal to 0. If I get that 1 to the other side, is equal to 1. And I have to divide both sides by 2, which means cos x is equal to a half. If I take an arc sine of both sides, I'm left with x is equal to arc cosine, of a half, which I believe will be the opposite of 30 degrees, which in terms of 90 degrees, which will be 60 degrees, which is pi over 6 times 2, which is pi over 3. But let's confirm that. What's the arc cosine of a half? The arc cosine of a half, I'm saying, is going to be 60 degrees. By the way, you can switch your thing here to radians, but it'll give you the decimal radians. Whatever gives you the radians, you have to divide by pi to see what the pi radians are. So let's leave it in gradients. I'm going to go to trig, second function, arc cosine. Oh, what did I do wrong there? Let's try it again. .5, second degree, trigonometry, second degree, arc cosine. Oh, I did something wrong. Oh, no, I didn't. 66 out of 90 degrees is 2/3 of 90 degrees. Two-thirds of 90 degrees, which is pi over 2, is 2 pi over 6, which is pi over 3. So I still got the right pi. It's weird that it said 66 degrees, though. Let's find 60 degrees cosine. Yeah, no, it should be 66 degrees. The arc sine of 0.5, arc cosine of 0.5 is 60 degrees. My bad. I don't know where that's 66, but I got it right. For some reason, my calculator was spitting out wrong. Oh, and it's important to always notice this because sometimes that's tricky, but in this case, they're saying in 360 degrees. Oh, actually, you know what? Good point. Good point. My mistake. So this first one, I discovered that sine x is equal to 0.5, and I discovered it's 35 degrees. But this result's positive. This result's positive, and I determined it's 30 degrees, which is pi over 6. But sine can also be positive over here, which means I'm talking pi over 6 there. But I always measure things based on the terminal angle, so I have to take 2 pi, sorry, 1 full pi, and subtract pi over 6. So pi minus pi over 6 is clearly 5 pi over 6. So that means there's another angle, not only this one, but there's also that one, 5 pi over 6. That's my big mistake on this one, my bad. I also determined for this one that the answer was 60 degrees. And it was positive 60 degrees. I had cos x is equal to positive 1/2. But cosine can be positive in this quadrant, and cosine can be positive in this quadrant. So I indeed figured out the first one, pi over 3, but I should have also figured out this one over here. Now I'm always measuring, though, the terminal angle, so I have to take 2 pi and subtract pi over 3. 2 pi in 3s is 6 pi over 3. Minus pi over 3, which is clearly the blue angle is all the way around to there is 5 pi over 3. So it's important, and that's the thing you got to watch out for. There's always 2 angles, and that's going to be very important for solving some of these. So that's it for now. I'll go to 5.1, which is all about E. Those were important to practice.